In this mini lecture we will discuss conventional alternatives to fossil fuels as an energy source. Specifically we will discuss nuclear power, bioenergy, and hydroelectric power. After reading Chapter 20, watching this video or reading the transcripts that go with this video, and watching the other assigned videos and activities for this chapter, you should be able to discuss the reasons for seeking energy alternatives to fossil fuels, summarize the contributions to world energy supplies of conventional alternatives to fossil fuels, describe nuclear energy and how it's harnessed, outline the society debate over nuclear power, describe the major sources, scale, and impacts of bioenergy, and describe the scale, methods, and impacts of hydroelectric power. Fossil fuels were the driving force in the Industrial Revolution and helped create the material prosperity we in the U.S. enjoy today. As you can see from the pie chart on the left, our global economy is predominantly powered by fossil fuels. Specifically 81% of our energy comes from coal, natural gas or oil. Examining the chart on the right, you can see that these three energy sources supply 2/3 of the world's electricity. However, if you look closely at the chart on the right, you'll also notice that the nuclear power and hydroelectric power contribute nearly 30% of the world's energy source for electricity. In this mini lecture we will examine nuclear, hydropower and bioenergy as conventional energy alternatives that may be able to help us move away from relying so heavily on fossil fuels for energy and electricity. In the other mini lecture for this week we will examine the new renewable energy alternatives, specifically wind, solar, geothermal, ocean energy, and hydrogen cells. As with other energy sources, conventional and new renewable energy alternatives are used to provide energy to 1. Generate electricity, 2. Heat air or water, and 3. To fuel vehicles. They have a great potential, however so far they have played a very minor role in most economies. Currently we obtain about 1% of our global energy from renewables. While not renewable, nuclear energy is an alternative to fossil fuels and is the main non-renewable alternative. Notice in pie graph B that nuclear energy is the main non-renewable alternative, providing 19% of U.S. electricity generation. The two of the most well-established and widely used renewables include biomass and hydropower. Other renewables include solar, wind, geothermal, and ocean energy, all of which we will discuss in the Chapter 21 mini lecture. These energy sources are referred to as new renewable energy alternatives. Nations vary in the amount of renewable energies that utilize. In the U.S., most of our renewable energy comes from bioenergy and from hydropower. As of 2012, wind energy accounted for 15% of U.S. consumption of renewable energy, solar energy accounted for 2.8%, geothermal accounted for 2.6%, and hydropower and bioenergy accounted for 30.4% and 48.9%, respectively. Clearly we are relying more heavily on biomass and hydropower. Wind, solar, and geothermal combined account for just 20.8%. Altogether renewables account for only 9.3% of U.S. energy consumption. Renewables account for 12.4% of U.S. electricity generation. While these numbers are small, it's important to note that renewables are growing faster than conventional energy sources. Wind power is growing at 50% per year and nations are looking for ways to move away from fossil fuels while ensuring a reliable energy supply. As profitable and beneficial as these fuels have been, there are significant reasons to switch to alternative energy sources, especially if those sources are renewable. To begin, fossil fuels, as we have discussed at length, cause a substantial amount of air pollution that both causes health problems and contributes to climate change. Switching to alternative fuels can alleviate these problems. Furthermore, many renewables are inexhaustible on society's timescale. Phasing out fossil fuels in favor for conventional alternative and new renewable alternatives will also diversify energy sources that economies around the world rely on. Renewable energy sources will also reduce price volatility, reduce dependence on foreign fuel, and create green-collar jobs due to the need for design, installation, maintenance, and management of renewable energy technologies. Clearly, there are many reasons to make the change from a fossil fuel-based economy to a renewable energy-based economy. Nuclear power has an interesting history and current standing in the modern debate over energy. On one hand, it has the significant benefit of being a clean fuel that produces no air pollution or greenhouse gases. However, nuclear power's promise of solving global climate change while still supplying us with energy is complicated by the fact that nuclear weapons are a real and significant concern, disposal of radioactive waste is still an unsolved problem, and nuclear accidents, such as Chernobyl and Fukushima, can cause significant and long-term damage. As such, public safety concerns and the costs of addressing these concerns has constrained nuclear power's spread. Nuclear energy is the energy that holds together protons and neutrons within the nucleus of an atom. Review the first part of Chapter 2 if you are unclear on what the terms proton, neutron, nucleus and atom mean. Nuclear energy is harnessed by converting it into thermal energy inside a nuclear reactor, which is a facility or system contained within a nuclear power plant that controls and sustains nuclear fission. Nuclear fission is a nuclear chain reaction where the atomic nuclei is split, seen in the upper center of this slide. We use the element uranium for nuclear power because it is radioactive. Specifically, we use radioactive isotope uranium-235 for nuclear fission. Radioactive isotopes, or radioisotopes, emit subatomic particles and high-energy radiation as they decay into lighter radioactive isotopes, until they ultimately decay into stable isotopes. Some people mistakenly use the terms nuclear fission and nuclear fusion interchangeably, however these terms do not mean the same thing and you should understand the difference. While nuclear fission is a reality and we use this reaction to generate nuclear power, nuclear fusion is not yet a reality. Nuclear fusion is the process that drives our sun's vast output of energy and is the force behind hydrogen bombs, which are thermonuclear bombs. Nuclear fusion involves forcing together the small nuclei of lightweight elements under extremely high temperature and pressure. In the upper right-hand corner of this slide I've provided you an image of a hypothetical nuclear fusion reaction. Here you see the hydrogen isotopes deuterium and tritium being fused together. The result from this fusion is an atom of helium, the release of a free neutron, and the release of a tremendous amount of energy. While this reaction has a great amount of potential to provide us energy, scientists have not yet been able to fuse atoms together without using more energy than the reaction produces. This means there is a net loss of energy, the ROI is negative, and this process is therefore not currently a viable option as a source of energy. A figure of a nuclear reactor is featured on this slide below the figures of nuclear fission and nuclear fusion. Fission occurs in the nuclear reactor core. There are fuel rods in the core that are submerged in water to keep them cool and to slow the neutrons to initiate a chain reaction in uranium-235 in the fuel rods. Control rods absorb excess neutrons to regulate the reaction. The purpose of controlling this reaction is to heat water to generate steam to turn a turbine and ultimately turn a turbine to generate electricity. There is an excellent short video in the Concept Videos for Chapter 20 folder for this week that explains how nuclear energy works. Please watch this video if you need further clarification on this topic. One reason why nuclear energy is still a hotly debated issue is because we still do not have a solution for the waste generated by nuclear power plants. Currently, nuclear waste from power generation is being held in temporary storage at nuclear power plants across the world. Spent fuel rods are sunken in pools of cooling water to minimize radiation leakage, as seen in the top left of this slide. However, most U.S. plants do not have enough space to accommodate this type of storage, so they are now storing waste in thick casks of steel, lead, and concrete, as seen in the bottom left of this slide. In total, U.S. power plants are storing nearly 70,000 metric tons of high-level radioactive waste, which is enough to fill a football field to the depth of 21 feet. Additionally, there's also even more low-level radioactive waste. Currently, high-level nuclear waste is held at more than 120 sites spread across 39 states. See the map in the bottom right of this slide. The Yucca Mountains were a proposed site for a centralized site for disposing of the nuclear waste in the U.S., however political forces largely defused this option between 2010 and 2013. One thing to consider is the advantages and disadvantages of centralized nuclear waste storage and disposal. While a remote, centralized site would greatly reduce the number of sites with nuclear waste disposal and storage-related risks, we also must account for the fact that nuclear waste would have to be transported across the country via rail and truck. Transportation of the waste could potentially put even more people at risk. Clearly there is not a simple solution to the problem of nuclear waste disposal. The other major concern with nuclear energy is the risk of a large accident. The three main events that have been most influential in shaping public opinion about nuclear energy are 3 Mile Island, Chernobyl, and Fukushima Daiichi. 3 Mile Island was a nuclear power plant in Pennsylvania that had a meltdown in 1979. A meltdown is when an accident in the nuclear reactor causes damage to the core due to overheating. Essentially, the temperatures inside the reactor core rise to the point that the metal surrounding the uranium fuel rods melts, which causes radiation to be released. The accident at 3 Mile Island was caused by a combination of mechanical failure and human error. Citizens living near 3 Mile Island were evacuated, and thankfully most of the radiation remained trapped inside the containment building. For this reason, 3 Mile Island is considered a near miss in that the emergency could have been far worse had the meltdown proceeded through the entire stock of uranium or if the containment building had failed in some way. Chernobyl is largely regarded as the world's most severe nuclear power plant accident. Chernobyl is in Ukraine, but at the time it was part of the Soviet Union. The Chernobyl power plant exploded in 1986, releasing radioactive debris into the atmosphere and surrounding communities. This accident was the result of both human error and unsafe reactor design. The accident killed 31 initially, but caused thousands to become sick either with cancer or other radiation-related illnesses. In total 100,000 people were evacuated. After the accident, an area with a 19-mile radius from the plant was blocked off. This area still remains uninhabitable and is barricaded off as it is still unsafe to enter the area. The most recent nuclear accident occurred at the Fukushima Daiichi nuclear power plant in eastern Japan following the 2011 Japanese earthquake and tsunami. The earthquake shut off power to the plant and that tsunami flooded the plant's emergency-powered generators. Without power, the engineers in the plant could not use moderators and control rods to cool the uranium fuel. The consequence of this was that the fuel overheated and the fission process proceeded uncontrolled. While Mother Nature caused the damage that led to the meltdown at Fukushima Daiichi, many researchers have reported that the accident could have been prevented if the plant had been updated in accordance with state-of-the-art safety standards and approaches. In this slide you see Table 20.2 that displays the risks and impacts of coal-fired power plants compared to nuclear power plants. Read this table and consider where you stand on this issue. Specifically, would you rather live near a nuclear power plant or a coal-fired power plant? Let's move on to the next conventional energy, bioenergy. Bioenergy, or biomass energy, is the energy obtained from biomass. Biomass is organic material derived from living or recently living organisms, such as wood, charcoal, agricultural crops, and manure. Over 1 billion people use wood for heat, cooking, and light. This occurs mainly in the developing countries. In developed countries we use bioenergy for biopower, which is when biomass sources are burned in power plants to generate heat and electricity. Many types of biomass are combusted to generate electricity. Common sources of biomass for biopower are waste products of industries or processes such as woody debris, pulp mill waste, and crop residues. Other waste sources for biopower include animal wastes from feedlots and organic waste from landfills. Up to 15% of the coal in some coal-fired power plants can be replaced with biomass, such as wood chips, to allow the plant to generate energy with less pollution. The process of incorporating biomass into coal-fired power plants is called co-firing. Co-firing is a relatively easy and inexpensive way for utilities to expand their use of renewable energy. We also harness biopower through gasification, which is when biomass is vaporized to create a gas that can be burned as a fuel to generate heat and electricity. Currently, much of the biopower produced comes from power plants that use cogeneration, which is when the excess heat produced by a power plant is captured to heat nearby homes and offices, as well as to produce other kinds of power. Bioenergy crops are usually fast-growing plants like willow trees, bamboo, and switchgrass. As Table 20.3 in this slide illustrates, there are a diversity of bioenergy sources, which means we have a variety of ways to address our energy challenges. However, it's important to consider the source of biomass as we evaluate the sustainability of this type of energy source. Biomass is renewable only if it is not overharvested and if the resources invested to grow the biomass are from sustainable sources. Overharvesting of biomass sources causes deforestation, erosion, and desertification. Biomass energy can also be used to create biofuels, which are liquid fuels used to power automobiles. The two main types of biofuels are ethanol and biodiesel. Ethanol is a biofuel made by fermenting carbohydrate-rich crops, such as corn. Ethanol has been added to U.S. gasoline to reduce emissions. In 2012, over 13 billion gallons of ethanol were made in the U.S. from corn. Ethanol production is experiencing a huge boom in production, largely due to congressional mandates to increase ethanol production. About 40% of U.S. corn goes to making ethanol for fuel. Ethanol is mixed in with gasoline up to 10% by volume, however some vehicles are being produced to run entirely on ethanol. There are also flexible fuel vehicles that run on E85, which is a mix of fuel that is 85% ethanol and 15% gasoline. While there are 9 million U.S. cars that use E85, most gas stations do not yet offer this fuel. While ethanol may seem like the golden solution to our energy problem for the transportation sector, what few do not realize, including most of Congress, is that growing corn for ethanol requires nearly as much energy as it produces, and there are other significant environmental impacts of growing corn for fuel. Specifically, growing corn impacts ecosystems because we have to convert natural land to agricultural land. Ethanol production requires significant inputs of pesticides, fertilizers, and irrigation. Ethanol competes with food and drives up food prices, and growing corn requires fossil fuel inputs for equipment, pesticides, fertilizers, and transportation to processing plants. When you consider all of these costs associated with ethanol, the ROI is about 1.5 to 1. This should tell you that ethanol is incredibly inefficient as an energy source. The other type of biofuel is biodiesel. Biodiesel is produced from vegetable oil, cooking grease, or animal fat. The oil or fat is mixed with small amounts of ethanol or methanol in the presence of a chemical catalyst. Biodiesel reduces emissions, has good fuel economy, is non-toxic and biodegradable, and costs a little more than gasoline. Biodiesel can be sustainable, depending on the oil used. While oil from used cooking oil would be sustainable, like ethanol, most biodiesel comes from earmarked crops, which means that biodiesel has many of the same problems as ethanol fuel. While conventional ethanol and biodiesel have their downsides, novel biofuels are being developed to eliminate some of the problems associated with conventional biofuels. For example, algae are now being used because they produce lipids that can be converted to biodiesel. The carbohydrates algae produce can also be fermented to make ethanol. Algae can also be used to develop a variety of other fuels. Algae grow fast, can be harvested every few days, and can be grown in ponds, tanks, photobioreactors, or in vertical growth setups. Another advancement in biofuels is cellulosic ethanol. Whereas ethanol production requires the use of a food crop, researchers are refining methods to produce ethanol from structural plant material that has no food value, such as corn stalks. If this process was developed to the point of commercialization, we could make ethanol from low-value crop wastes, such as corn stalks and corn husks, rather than from high-value crops. This would mean we wouldn't have to grow our fuel, rather we could just put the waste product from a food source to better use. There are some benefits and drawbacks to biopower. Biopower increases efficiency and waste recycling. It reduces CO2 emissions, and it reduces sulfur dioxide emissions when used to replace coal. However, burning crops in areas away from where they originally grown deprives the soil of nutrients, which means the soil is progressively depleted. Then there is the question of whether or not bioenergy is carbon neutral. In principle, biomass energy releases no net carbon. However, in practice, burning biomass is not carbon neutral because of the forests are destroyed for cropland to grow bioenergy crops, or if fossil fuels used in the cultivation of the crops through fertilizers, transportation, use of tractors, or use of pesticides. It should then not come as a surprise that international climate change policy does not encourage bioenergy approaches because in practice they are not sustainable. The final conventional energy alternative we will consider in this mini-lecture is hydropower. Hydropower uses the kinetic energy of moving water to turn turbines to generate electricity. There are three approaches to hydropower: the storage technique, the run-of-the-river technique, and the pumped storage technique. In the storage technique, water stored in reservoirs behind dams and then passes through the dam and turns turbines. The storage technique provides a steady and predictable supply of electricity, even when natural river flow is low. Large dams can provide a substantial amount of hydroelectric power. The run-of-river approach generates electricity without disrupting the river's flow. Water is diverted from the river via a pipe or channel. The water flows through a powerhouse, which contains a generator and turbine, and then the water is returned to the river. This method is useful in remote areas away from electric grids. The downside of this method is that the electricity generated is less reliable because you can't guarantee reliable water flow. The benefit of this technique is that it minimizes impacts that come with damming a river. For example, the run-of-the-river approach doesn't alter existing flow or water levels. The pumped storage approach is when water is pumped from a low reservoir to a high reservoir and flows downward through a turbine. The water is typically pumped up to the high reservoir when demand for power and electricity prices are low, such as during the nighttime. Then when demand and prices are high, water is allowed to flow downhill through the turbine to create electricity. This would likely be during the daytime. The pumped storage approach can help to even out power supply when paired with intermittent sources like solar and wind power. Hydropower has some clear advantages over fossil fuels for producing electricity. It is renewable. As long as precipitation fills rivers, we can use water to turn turbines. It is clean, meaning no carbon dioxide is emitted when we generate electricity via hydropower, and hydropower is efficient. It has one of the best ROI ratios at 100 to 1. For reference, coal is about 80 to 1 and oil is about 11 to 1. But there are some significant disadvantages to hydropower. As we've discussed before, damming rivers destroys wildlife habitats. When dams are built, upstream areas are submerged and downstream areas are starved of water. Natural flooding cycles of rivers are disrupted. Downstream floodplains don't get nutrients. Damming causes thermal pollution, and dams block passage of fish, fragmenting the river and reducing biodiversity. While dams have helped many nations, such as Canada, Brazil, Norway, Austria, Switzerland, and the US develop, hydropower isn't likely to expand much more because most of the world's large rivers have already been dammed. Specifically, 98% of US suitable rivers have been dammed and the rest are protected. Furthermore, people have grown aware of the ecological impact of dams. There is no movement to eliminate dams and restore streams to their natural state. That concludes the first mini-lecture on conventional energy alternatives. Please review the weekly outline and complete the activities for this week per the schedule set forth in the outline.